So as we have discussed in the previous parts of lecture, that we are going to assume that the parameters W are now random variable, is a random variable, with some prior distribution P of W given some hyperparameters gamma and lambda. So here these are not random variables, they are the hyperparameters. That controls the distribution of W. So now the prior distribution of W is given by P of W given gamma, lambda, the hyperparameters. Now let's assume this is the so this is a prior belief of W without observing any data. So now let's assume that we observe a data set D with m data points xi and yi, where I goes from 1 to m. So now we can ask ourselves a question, given this prior distribution and given the data set, what is now the posterior distribution of the parameter W? So what is the distribution of W given the data set and the hyperparameters gamma and lambda, right? So here we can use a Bayes theorem, right? So this distribution is given by, is going to be directly proportional to the distribution P of the data, which is P of y given x, given the parameters W, times the prior distribution of W given the hyperparameters gamma and lambda. So here we have just used the Bayes theorem, which says that the prior distribution P of W given the xi's and the yi's. So we are just representing all the xi's with a matrix X and representing all the yi's with a vector Y, given gamma and lambda, is directly proportional to P of y, the same notation, P of y given x comma W times the probability of P of W given gamma and lambda. And since this W is a continuous variable, so here we can see that the denominator is given by the probability distribution of B, which is nothing but marginalizing the numerator, the conditional distribution of P given A times the probability of A, by marginalizing it over A. Right. So here we can place the equal sign, P of W given x comma y comma gamma comma lambda is equal to P of y given x comma W into P of W given gamma comma lambda over. So now since W is a continuous variable and is it's not discrete, so the summation would be replaced by the integration. So this would be integral over all the values W, P of y given x comma theta into P of theta given gamma comma lambda times d theta. Right. So we're integrating it over the domain of W, right? Or we can just replace it this theta by W, and this would be then dW, right? So just for the sake of completeness, although this denominator doesn't play any role, this is just a normalization term. So this ensures with this normalization, if we now integrate this distribution, if we now integrate this entire distribution over W, with this normalization term, the denominator, this will come out to be 1. Right. So this is just a normalization term. It doesn't play any role in the optimization formulation. Right. So we can, so oftentimes we'll just like instead of just complicating the notation, we'll just assume we just use a proportionality. We assume that P of W given X, Y, gamma and lambda is proportional to the P of Y given X, comma W times P of W given gamma, comma lambda. Right. And now, so basically the distribution of W when we had no data set was just given by our prior belief, which was we considered two kinds of distribution in the previous part of the lecture, which was one was normal distribution, one was the Laplacian distribution. So if someone asked you that was the most explainable, most plausible value of W given the prior information that you have without any data, let's say okay, the most plausible value of W or the most probable value of W is a vector of zeros, right? But now since you observe the data set, now the same value of W that you are selecting based on the prior belief should also satisfy the data, right? It should minimize the error in the data itself. So what is the distribution of W now after observing the data? So this is a posterior distribution of W. We'll just write it again to avoid clutter. So P of W given X, Y, gamma, lambda is proportional to P of Y given X, comma, W times P of W given gamma, comma, lambda. Here you can see we have no semicolon. It means that the W is a random value. The conditional distribution of Y is dependent on both X and W. Right. So this is our prior distribution. The prior knowledge about the pointers W. And this, if you remember the previous lectures, this is nothing but the likelihood function. And the likelihood into prior is posterior distribution. And if we divide by the normalization term, then we can just replace the proportionality with an equal sign. Right. So since this normalization term doesn't play any role, we'll just like have the proportionality sign. Posterior is directly proportional to the likelihood into prior, and this likelihood is nothing but, assuming that each of the noises are IID, this is nothing but multiplication of the individual probabilities. P of Yi given Xi and W, and this would be the prior distribution. Let's assume if this is a normal distribution or any distribution for that matter, and this would be P of W given gamma, comma lambda. So now you can see the posterior distribution has to explain both the likelihood as well as take the prior information into account. So we here to derive this formulation we have nothing, we have used nothing but simple Bayes law. Right. So now you may ask, having this posterior distribution, over the parameter after observing the data set is given by P of W given. So we can just write X and Y combinedly as the data set, given the data set and the hyperparameters. So the hyperparameters are not random variables, there is just some hyperparameters that are controlling the distribution. So given the data set and the hyperparameters gamma and lambda, let's suppose we observe a new value x hat, new input x hat. Then how can we predict the y hat, right? So in the earlier, when we used the MLE estimate, we saw that we could compute the estimate of WMLE, and when there was a new input variable x hat, we could just plug this x hat in the FWMLE of phi of x hat to obtain the resultant y hat values. But now the advantage of this Bayesian formulation is that instead of getting a single y hat prediction value, we can get the entire distribution over all the possible values of y hat. So now we may ask ourselves a different question, right? So rather than asking a question, so the first question was, in the MLE setting, given some x hat, what is corresponding y hat value? So this is a question we can ask over here as well. But then there's a question number 2. Given x hat, what is the distribution of y hat given x hat and the data set that we have observed so far? We have a set of m data points, xi, yi. So I'm just writing superscript m to denote that there are m data points in the data set. So now we can ask a different kind of a question, right? So in the first case, in the earlier lecture, in the least squares regression, even the processing interpretation, we asked ourselves a very different question. What is the y hat for given x hat? Now, a much powerful question is that given x hat, is there a way to predict the entire distribution over the possible values of y hat? Can we do it? And the answer is yes, and that's why we are having this lecture. So the posterior distribution of y hat, the distribution of y hat, conditional distribution given the x hat and the data set that we have observed so far, which is a set of m data points, is simply P of y hat given x hat and w times the posterior distribution. So now here we will make use of this posterior distribution. So from the data set, whatever we had, we computed the posterior distribution of w, right? So now we can use this posterior distribution of w, P of w, given the data and the hyperparameters gamma and lambda, and we can integrate it over w. So as you can see, the Bayesian formulation is much more powerful formulation. So using the Bayesian formulation, you can compute the entire distribution over the target values y hat. Now you may ask, like, what does this equation practically represent? How am I able to, how am I going to understand what is the practical implication of this equation, right? So let's try to understand what this equation is actually, what information does it convey to us, right? So let's assume that you have, we consider that yi's are given by some functional mapping phi of xi plus the small error, right? And we had we assume that this error or IDs and have some distribution, right? So we also saw that the expected value of yi given xi is nothing but the functional mapping of phi of xi, right? And likewise, let's suppose we don't have any data set, right? We just have the prior distribution, prior P of w given gamma and lambda. Given that this is the only distribution that we have, and let's assume that this is a normal distribution with mean 0 and covariance lambda inverse I. Right. Then, if we don't provide you any data and we ask you that this is the only prior information that we have, Now, what is the most plausible value of y hat, right? What is the most plausible value of y hat given x hat and the w, right? So you can say that this is 0, right? Or you can say the expected value of y hat given x hat and the prior distribution of w is phi of x hat transpose times w is drawn from the prior distribution. So this prior distribution says that the most plausible value of w is 0. So what is the expected value of y hat given x hat? This would be nothing but 0. So 0 seems to be the most plausible value of y hat. But now let's assume that you observe one data point, right? You observe, now we are throwing data set at you one by one sample by after the next. Sorry, one sample after the other. So let's assume we give you x1 and y1, where y1 is not equal to 0, right? So now, if you take the prior distribution into account, the prior distribution will say that the most plausible value of w is 0, and that's why the most plausible value y hat, this predicted value, should be 0. But what you're observing is that the most plausible value y1 hat is 0. But what you're observing in the data is that y1 is not 0. It means that our prior knowledge about the w, although it says that okay, that the values of w should be smaller, but it's not that accurate, right? It means that the w, the parameters w should be shifted away from 0, somewhere else, maybe to the left of 0, to the right of 0, but not exactly 0, right? So this is exactly what we get by computing the posterior distribution of the w. So remember, the posterior distribution P of w given the data and the hyperparameters gamma and lambda is dependent on both the likelihood of the data, which is nothing but multiplication of the individual probability of the data. So if you have just observed one sample, then it has to explain P of y1 given x1. Sorry, x1. Sorry, the I, there's no I, it's just like 1. Just assume we have observed just the first data point. So now this posterior distribution has to explain both the likelihood, that is P of y1 given x1, and the choice of w times the prior distribution that we had over w. Right. Now let's suppose we observe another data point, x2 and y2. So now this posterior distribution has to explain both the likelihood, the probability of the data, the probability of the observation of the data, and take the prior information into account. Right. And likewise, we can generalize for the m data points. So if we have observed m data points, so now the posterior distribution takes into account the likelihood or the probability of the observation of the target values given the input values and the value of the parameter, that is times the prior information. So now you can see, earlier we were just using our estimate of w using the likelihood, but now we are satisfying the likelihood. We still want to increase the probability of the observation of the data, but still we are also biased by this prior information or the parameters w that we had. And this is exactly what this equation represents. So why, you may ask the question, the natural question is, why is this distribution of y hat given x hat is also dependent on the data, right? Why is the distribution is dependent on the data? This is because the posterior distribution of w is directly controlled by the data set. So the more the data that you observe, the better and better you will get at predicting the true value of W that is generating this data, while also taking into account the prior value of the W. So if we had observed no data at all, this would be just given by this distribution, and this would be the most the distribution of Y will just follow the distribution of W, right? So for example, if you select W equal to 0, then the Y hat will be 0, and that will be the highest probability. Likewise, if you select some value of the W as W hat, which is the prior, then the probability of that W hat would directly control the probability of the value Y hat, right? And that is why after you observe the data, the resultant posterior distribution will change, and taking that posterior distribution into account, we can predict the entire we can compute the entire distribution over the values of Y hat, right? So this is the Bayesian formulation, right? So what the Bayesian formulation says is that given the prior, we have prior P of W given gamma comma lambda and the data set. We compute a posterior distribution P of W given the data set, the posterior given gamma and lambda, the hyperparameters, is directly proportional to or equal to, I mean, we can just, because the denominator is normalization term, we can ignore that we had discussed earlier as well. Here's write equal for the sake of simplicity. Or we can just write it again using the equal sign, but with some constant, is equal to the probability of the data, right? The likelihood Y given X comma W, there's the data, times the prior P of W given gamma comma lambda, divided by some constant. So now, once we have this posterior distribution, when a new variable X hat arrives, we can predict the entire posterior distribution, entire conditional distribution of Y hat given the X hat and the data as integral over all W P of Y hat given X hat comma W into P of W given the data comma gamma comma lambda. So we use this posterior distribution to compute the conditional distribution of Y hat given a new input data point X hat, right? But there's a problem, right? This integral, assuming that W is an n-dimensional real vector, this integral is very hard to compute, right? We can compute this integral perhaps when W is a scalar and only in some special cases. But when W is an n-dimensional real vector and these distributions or any general distribution, it's not easy to compute the conditional distribution Y hat given X hat in the data. So now theoretically it all sounds very good that okay, we have the prior, we have the likelihood function, then we can compute the posterior distribution, and then given some new input data points we can compute the conditional distribution of Y hat given X hat. But in practice it doesn't work so well because this integral is very hard to compute, right? So now the next obvious question is, given the prior information and the likelihood, right, can we compute a single optimal value of W that takes both the likelihood and the prior into account, so that we call it W nu, right? Can we compute this W mu that maximizes this posterior distribution, right? So one of the obvious choices of the W now is the one that maximizes the likelihood, right? That maximizes this likelihood as well as the prior, taking the, so there's a trade-off between the likelihood and the prior, right? So it takes the prior into account, it takes the likelihood into account, and now can we compute a W that maximizes this posterior distribution? And the answer is yes. And this new estimate, which maximizes the posterior distribution, is known as maximum a priori, a posteriori probability estimate, or WMAP for short. So, we can write it again simply as WMAP maximizes this posterior distribution, and it takes into account the likelihood of the data given the parameter values and the prior information of the parameters, right? So in the next part of the lecture, we are going to see what different kinds of distribution, that is namely the Laplacian and the Gaussian distribution, what kind of effect they have in the resultant optimization problem.